Fall, the prettiest season on the Sierra College campus. I think it's the prettiest season because we have all these beautiful Chinese pistache trees and maples. The colors are just brilliant, especially on a cloudy day like today. This was a couple years ago, maybe, or last year. It was a sunny day when there's no clouds in the sky. The trees are still pretty, but when there's clouds, they pop like they're plugged in. Do you agree? Do you think fall is the prettiest season at Sierra? All right, so today we'll continue chapter 5, stereochemistry. Oh, wait, I'm getting a text. Hold on just a second. What's it say? Oh, what the heck? I wanted it to be timed better. I'll let it get. I don't know how to, I thought I had this worked out. Okay, there it is. Wait, I'm getting a text. Tell the class to number there. That's not how you spell there. Carnus? No. Carbons. Oh, yeah. Number the carbons. Yeah. Let's send it with the screen effect. Okay, yeah. So I can't emphasize it enough. If you number your carbons, you can increase your grade in the class by like 5–10%. If you just number your carbons, because so often students will miscount. They'll leave off a carbon or they're out of carbon. And when they do that, it could change the problem in a way that makes it extremely difficult for them. And they just, that may like get stuck on that problem and not have time for other stuff or just wear themselves out. Or they could change a problem that's like difficulty of like a 7 out of 10, and they make it a difficulty out of 1 out of 10. Now, how do I grade it? Like, oh, you wrote your own question now, and that's a little way easier than the one I was asking. So number your carbons, keep track of them. All right, and then today you can come into the lab and work early as usual, today and tomorrow. So you can come in about 1 on Mondays and Wednesdays and work early. Tuesdays, Thursdays, you come 9. And assignment due dates. So the homework C, chapter 3 and 4 is due today, and I'm updating homework D, chapter 5, which we're talking about today. I'm updating that now as we speak. I'll get that up soon. And then this exam this week is actually now pushed back to Monday, Tuesday, you should all know. So there's no exam today. I wonder if anybody will show up today. I'll like, okay, I'm ready for the exam. That would actually be a good thing if they're ready early. And I've already told you all this stuff, so I'll just go through it quickly. I've already written the exam. You have extra time if you want it. You can come early and come in quietly when you come early. And exam details, outcomes from chapter 2, 3, 4, and then maybe some from 5, that just the definitions. And then those kind of problems should be on there. So this stuff you should do well with. You should just, this is, it's coming. Practice, practice, practice. And yeah, same here. And then we talked about how I like this trick of it's easy to view the Newman from this side, but if you're viewing it from the other side, you got to be careful. So let's review really quick. So if I'm viewing from the back side and I draw my 2 circles with the dots, the owl eyes, is carbon 2 on the right or the left? Owl eye, viewing from this side. So what's going on here? Whoa. Yes. Yeah, the carbon 2, it looks like it would be on the left, but when you're viewing it from the other side of the chair, it's going to be on the right. All right, so if you're confused about that, look at the last lecture. I go over it. And review your PKs, your NMR data, your NMR trends. And all you have to do is just sit down with a piece of paper and a pencil, go to these animations and click through them a couple times maybe, and then try to recreate the whole thing. Carbon, the proton, the carbon, the iron. I think if you spend like 10 minutes on this, maybe more, not that much more, you can get them all memorized again. And it'll be easy to memorize them now because you've already memorized them in the past. And then look for these trends, the carbonyl trends, and the proton NMR is the most useful spectral data on these problems, right? Carbon helps, proton NMR is the best. The IR helps a lot too, but proton tells you the most because of all the coupling and that. So you should get good at noticing like, oh, a quartet triplet. That's ethyl or isopropyl. Big 6 hydrogen doublet, isopropyl, and if carbon, all that stuff. I already went over it. Okay, and then prepare for lab this week outside of lab by reading intro material, so you can use most of the lab time doing wet chem. So if you have if you spend 30 minutes reading and getting prepared when you come into lab with right at the wet chemistry part, then you're going to be able to really get going on that. Okay, so that's my intro. Yeah, that's right, Ryan. Yeah, the videos can be long, and if you're not comfortable watching them at faster speeds, it could take you a while. I want to make them shorter, but I think they're good. I don't know. There's just so much time in a day. Yeah, 1.5 speed works for me when I'm watching YouTube videos, but two times speed, the person has to be a slow talker. Yeah, thank you, Ryan. Yeah, I agree. Okay, so if there's no questions, we'll get going. Chapter 5, stereochemistry. Here we are. So we've defined stereoisomers. Yeah, we're going to review that again really quick. And let's do it once quickly with this PowerPoint slide, and then I'm going to do it on the Jamboard. This is something that's another one of those things you just kind of got to get in your head. So if I look on the step-by-step, oh, I've got the rotation practice. I want to point that out again. This is really good to do. I'm putting on this on homework 5 as a requirement. Oh, I didn't link it. That's weird. Let me see. You've seen this before. You saw it at the beginning of the year, but it's been a little while. So you'll want to do this again. Link. All right, there we go. What did I do? Link now? Apply. That should work now, right? Yes. Okay. So you remember this one? It steps you through visualizing these rotations. This is an excellent one. If you do this a few times, this chapter 5 material will be a lot easier to understand because you'll have a better understanding of the three-dimensional nature of this. And this is helpful for our course, of course. Our course, of course. I like that. But it's also helpful for biochemistry, looking at enzymes and how they react. And like I said before, dentists, they can look at things in a mirror and not be confused. Okay, so check that out. And then got some others I'll go through here, but I wanted to look at chapter 5 outline, yeah. I'm gonna do this one really quick. Okay, so this is the online version. Pre-animations. Slideshow. From current slide. God. Oh, that's the wrong slide. Oh my goodness. Oh, that's what it was. Okay. All right. So isomers, they have the same molecular formula. 2 molecules, same molecular formula, like say they're C6H12O2, something like that. They're the same molecular formula, but they're different structures than their isomers. And under isomers, you can have the constitutional isomers, which are more different than the opposite of the stereoisomers. So in the constitutional isomers, they don't have the same connectivity. So both of these, you can see you have 1, 2, 3, 4. We got this butane bastard gas. It's straight chained. And this also has 4 carbons, but it's the 2-methyl propane. And they both have the formula C4H, let me see, 4, 2N, 2 times 4 is 8, plus 2 is 10. So C4H10, because they have 0 degrees of unsaturation. So C4H10, C4H10. They're definitely isomers, but they're not the same molecules. They're not connected together the same, different connectivity. Those are constitutional isomers. Now, stereoisomers, they're more similar than constitutional. And they fall under the category of diastereomers, the ones that are, they're the same molecular formula because they're isomers, and they have the same connectivity. Like I have a 5-membered ring with a methyl on the 1, 2, and then the 3 carbon. So this is 1, 3-dimethyl cyclopropane. You got to remember the cyclo. Don't forget. A lot of times when students name cycloalkanes, they leave off the cyclo. So don't forget that. So this isn't 1,2-dimethyl pentane. This is 1,2-dimethyl. I mean, not 1,3-dimethyl cyclopentane. And then this one's also 1,3-dimethyl cyclopentane, but they're different because they don't have the same 3-dimensional arrangement of atoms. So this one's got two methyls pointing up, and this has 1 down, 1 up. So they are they're stereoisomers. But are they enantiomers or are they diastereomers? So they're diastereomers because they are what? What makes them diastereomers and not enantiomers? Does anybody remember? So enantiomers are stereoisomers that are mirror images. Diastereomers are stereoisomers that are not mirror images. That's right. So these are not mirror images. If I try to like spin this molecule around and stuff and draw a dotted line between them as a mirror, they're just not going to be mirror images. So they're diastereomers. And then enantiomers are also stereoisomers. So they got their isomers, same molecular formula, CHBClF, right? Br, bromine, chlorine, fluorine. And then this one's got the same formula, carbon, hydrogen, bromine, chlorine, fluorine. But they are mirror images. See how the F is looking at the F and the Cl is looking at Cl, HH. But if I try to superimpose them, they will not superimpose. Let me actually show you an example of that. So I've got a model here. Can you see? Yeah. Check me out in my little window. Is my little window too small when I do this? What do you think? Should I stop the screen share? Check the chat. So those of you, oh yeah, so flip your view. Well, you know what? I'm recording this though. I think I should. I just got to remember to start screen sharing again. Okay. So on my recording, it's bigger. Okay, so are these two molecules the same, first off? So, well, they have the same molecular formula if I consider the colors like different atoms, right? And if I try to, what's called superimpose them, I try to put the green on the green and the blue on the blue. So I've got that green on green, blue on blue. My yellow and red don't match up right, huh? Oh, but I can fix it. I'll get them to match. Watch, these are the same one. I bet they're the same. Let me do this. So red and yellow are matched, and then the green, green and the blue aren't matched. Oh, come on, don't rush me. I'll get it. Okay, so I'm gonna go green and blue. Green and blue match up. Yeah. Oh wait, no, right this way. There we go. I got the green and the blue, and so my I'll get it. Just give me a minute. Okay, just give me a minute. Just match. They're different. Just kidding. Yeah. So no matter how much you try, I make a joke of this because I want you to if you can do anything, any rotation of bonds, any moving of the, you can do anything that makes them all match up, then they're the same molecule. These ones I tried a bunch of ways. They're not the same molecule. So these are different molecules, even though they look so similar. They're different molecules. And are they mirror images? Let's see. If I hold it this way, as if there's a mirror between them, the blue, the green and the red are mirror images, and the yellow's pointing away. They're mirror images. Yeah, there's a mirror right down the middle between them. I can see that they're mirror images this way, or I can do it like this. I can see their mirror images. If you can see, hold it from the top. You see how they're mirror images that way. Or if I go like this, they're still mirror images. Lots of ways to show their mirror images, right? So these are mirror images. They're not the same molecules, same molecular formula. So they are enantiomers. Get back to my PowerPoint slide. It's the one. Did I close the PowerPoint? that, save it. Oh, I'm on the PowerPoint online. Ugh. There we go. Yep. So enantiomers are non-superimposable mirror images. Okay. Now let's go back to my Jamboard. Let's make sure we got these down really quick. So let's start. I'll flip it. Isomers. What are isomers? What is the same thing? What's the definition of isomers? What is this? I guess the definition, or what makes two molecules isomers? What has to be the same about them? With the same what? Same molecular formula. I feel like my capitalization, my shift for capitalizing is lazy lately. I'm never capitalizing when I want to. All right, so isomers are molecules with the same molecular formula. So let's try some of this out. So are these? Are those two molecules isomers? Let's check it out. What's the formulas? I got on this guy, I got C5. Since I said to number my carbons, let me number them. C5H. Oh, I know it's 10 because it's just 1 degree of unsaturation. It's just double the number of carbons, but I can count it up. 3, 4, 5, 6, 7, 8, 9, 10. And then this other one is also C5. H10 because it's 1 degree of unsaturation as well. So are they isomers? These two are isomers. And under isomers, are they constitutional or are they stereo? What do you think? Constitutional means their atoms aren't connected together the same. Stereoisomers, their atoms are connected all together the same. So these are definitely constitutional, not stereoisomers, right? Let's try some more. Actually, I can still do it on this page. I got room. Let's do these two. Are they isomers? They're both C4, oops, H8, huh? Because they have 1 degree of unsaturation. So they're definitely isomers. Yep. And then are they constitutional or are they enantiomers? I mean, stereoisomers. Are they connected together the same? Do they have like, they both have a methyl on the left, say, and then a CH, CH, then a CH, CH, then a CH3, CH3. Yeah, they're not constitutional. They are stereoisomers. Okay, are they mirror images or are they not mirror images? So if they're, say yes over here, no over here. So if they're, are they mirror images? Well, before I answer, actually, if they are mirror images, do you know what we call them? Enantiomers. If they're not mirror images, then they're diastereomers. So what are these guys? Are they mirror images? No, they're diastereomers. Whoa. Oh, that's cool. Oh, so they're not enantiomers because the answer is no. Diastereomers. They just differ in three-dimensional arrangement, and they're okay. So one more here. Let's do a couple more actually. Let's do. What about these two? Are they isomers? Do they have the same molecular formula? Yeah, they're isomers. They're both C4H8, 9, 10. So I doubled the 4 and added 2 because there's no unsaturation here, plus the O. C4H10, no, they're isomers. So are they constitutional or stereo? They are stereo because they're connected together the same, right? And then under stereo, are they enantiomers or diastereomers? So are they mirror images? So when I ask that, are they mirror images, things like that, you can flip molecules over and check to see if they're mirror images. You don't just look at them as I handed them to you on this, as I drew them, I mean, on the screen. Yeah, you have to like move them around to see if in any way I move them, twist them. If they're mirror images, they're mirror images. So for example, I can take and do the pancake flip on this guy. So I've got like a pancake spatula. Put like some, I don't know what I'm doing there. So that's the spatula. S-P-A-T-U-L-A, pancake. Okay. So if I do the pancake flip on this, it could look like this. And now they almost sort of, oh wait, I'll draw that hydrogen. They look almost like they're the same, molecule, but they're not. Oh, because you could tell they're not the same molecule, because if I slide this over on top of it, the OHs don't match up, right? They're not the same molecules. And if I look at these two, then these two are mirror images. Like this one, I know it's getting a little weird here. These two are mirror images. And make sure you understand, this right here is the same as this. I just did the pancake flip on it. So let me number my carbons, like I said. So if this is carbon 1, 2, 3, 4, when I do my pancake flip, I'm saying that this is now the carbon 1s on the left. Okay. And if you're having trouble noticing like, oh, this dashed is now wedged, how did that happen? Then you need to practice that rotation practice I talked about at the beginning of the lecture. That whole rotation practice really makes this a lot, like, makes it make sense. Okay, so back to our question. Is it a mirror? Are they mirror images? Yes, they're mirror images. So they are enantiomers. All right, let me trick you now. Are these isomers? So I said I'll trick you, and Ryan said it's not Halloween, but Halloween's trick or treat. There's no treat here; it's all trick. No, it's just kidding. It actually is kind of a treat to know that you can know, like, not to be tricked later on when the points are coming. So this is both a trick and a treat. So do you want? Are these isomers? So do they have the same molecular formula? First off, let's see. I got 1, 2, 3, 4, 5, 6, 7. C7. 7 times 2 is 14. Plus 2 more, 16.
We can't see what you're writing, Mark.
Oh, I never switched screens. These two. This is the trick one. Thank you very much. Yeah, so they're both, sorry about that. These are both 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. So they have the same formula. Are they isomers? So I see some people saying yes to isomers. I see some jumping ahead and going, oh, they're enantiomers. But it is Halloween, so wait. You just died on this one. This question is poisonous. So, because these, they're not isomers. To be an isomer, you need to have the same molecular formula and be different molecules. All right. These are not different molecules. These are the same molecules. What I'm getting at is if I take this one, right, and I look at it more carefully. I say, okay, I've got a methyl here and there's an H here, right? And now I'm going to rotate around this bond right here. Imagine a Newman projection, like looking down this eyeball, looking down that bond. I'm going to rotate around that bond, and let's rotate it. I'll start going slow. I'll go 60 degrees and then I'll keep going. We'll see what happens. Wait, what do I want to do? Yeah, no, I don't want to do the 60 degrees. I want to rotate it so this methyl that's wedged will be in the plane of the screen. Is that what I want to do? Oh my goodness, I'm blanking right now. Let's see, if I put that methyl on the plane of the screen, the other one will be dashed. Okay, yeah, that's what I wanted to do. So I rotated this. This way. And I only rotated it 30 degrees. So if I were to label these two methyls, I call this one A and this one B. Did I do that? What am I doing? I've taught this subject before. This isn't my first time. All right, back to rotating it around this way. Okay, so now I'm going to rotate this 60 degrees. Yeah, I had it 60 first time. So methyl A and B are changing spots. So this will be A now, and this will be B. Okay, finally. Now I'll do another pancake flip on this. Bring out this big spatula. Here we are at the Stereochem diner. What are you going to get? The hash brown or the fruit? You're getting the fruit. Okay, so I pancake flip. It's going to look just like this. This is still A over here, and this is B. Do you agree with that one? My pancake flipper is flipping like over this way. And then you should notice these two are the same. And if they're the same molecule, they're not isomers, then they're not enantiomers, they're not diastereomers, nothing like that. You know what? This isn't 60-degree rotation. This is 120. Woo-wee. Yep. Yeah, it's 120. What I did on that rotation is I took methyl that's wedged out and I rotated it into the position of B. Methyl A rotates to B, so B rotates to dashed and dash rotates to wedge. So there's a wedged hydrogen here, right? Maybe if I draw that, it'll help too. Wait, the dashed hydrogen becomes wedge, yeah. So there's a hydrogen right there. Okay, so yep, they're the same molecule. I tricked you. If I would have drawn this example up differently, if I would have drawn it up like this, you wouldn't have been tricked, I don't think. Watch. If I would have said, oh, yeah, is this the same as? Are those two the same or different? You'd probably quickly say, oh, they're the same. But because I wedged one and showed the 3D nature of that, you got confused. I'll be doing more practice like this, so you'll get better at it. Okay, let's go back to define stereoisomers. Okay, actually, before I do that, I do want to look back at this one again. Let's go through this quickly. Oh, no. Okay, I'm on that slide, current slide. All right, here we go. So isomers, they're different molecules, right? With the same molecular what? Formula. And constitutional isomers, also known as structural isomers, they're isomers, so molecules that are different with the same molecular formula. But what else makes them constitutional? They have different what? Different connectivity. And then stereoisomers, they have the same connectivity, but different spatial orientation. Ah, I answered that one for you. Okay, so here I have 1,2-dimethyl cyclohexane. Here I have 1,2-dimethyl cyclohexane. Now, what should I put out front? Oh, by the way, so these guys are this. Do they have the same molecular formula? Yes. Do they have the same connectivity? 1-methyl, 2-methyl? Yes. Are they the same in terms of their three-dimensional arrangement of atoms? No. Okay, are they the same molecule? No, so they're isomers, they're stereoisomers. Are they mirror images? Nope. So what are they? Enantiomers. If they're mirror, I'm sorry, diastereomers. Thank you. I don't know what my deal is today. I don't know, maybe I didn't eat enough breakfast. So they are diastereomers. So Santos, they are stereoisomers, they're diastereomers. Okay, so here we go. So I was prepared to just proctor an exam today. Just sit there and look like I'm staring at you while I daydream. That was my plan today. That's what I'm on. All right, so here we are. We've got the two, when they're both facing the same way like this, we actually call them something. We call them cis or trans. Yeah, cis. And when they're the opposite way, they're trans. And then a more specific nomenclature is this. We're saying one of them is R, one R, and the other one is S. This R and S I'm about to define, but I want to just go through these first. So ignore the one R, one S as of now, but you can see that, oh, look at now this one's one R, two R. So we'll see what those are, what those mean in a moment. Now, what about this next two here? Do they have the same molecular formula? Same molecule. Do they have the same connectivity? Methyl, CH, CH, methyl. Yeah. Do they differ, or do they have the same connectivity? Yeah. So they're stereoisomers. Do they, are they mirror images? They're not mirror images. So what are they? Diastereomers. And then this one here, it's called 2-butene. They're both 2-butenes. We'll learn how to name alkenes later, but it's kind of like butane, right? But it's butene. And now the 2 means that, okay, this is carbon 1. The alkene starts at carbon 2 and it goes to carbon 3. But if we say it starts at 2, we already know it goes to 3 because alkenes are just between 2 carbons are attached. Anyway, so now what do you think we call this 2-butene over here? Do you think we call it the cis or the trans 2-butene? This one's trans. They're on the opposite side, like when they're on the opposite side up here. And then so this one is called cis 2-butene. Yep. So these diastereomers are trans and cis butene. All right, then this guy, let's go through it. Enantiomer examples. So enantiomers are stereoisomers that are non-superimposable. What kind of images? Mirror images. So if you have stereoisomers that are mirror images, enantiomers, and then non-superimposable, that's a big word, huh? All that means is that if you take the two molecules and you try to put them on top of each other, they can't have everything match up. So they're basically, it just says they're not the same molecule. If two molecules like totally match up with each other in all ways, then they're the same thing. They're not different. They're not isomers. Okay, let's look at a couple. So this one here is called 1R, 1-phenylethanol, but the R thing we haven't defined yet. And then this one's the 1S, 1-phenylethanol. We haven't defined S yet. But can you see that they have the same molecular formula, same connectivity, and that they're mirror images? As long as they're different molecules, they're enantiomers. So let's look. If I take the R molecule and just drag it down here, it'll look the same, right? And if I take the S molecule and I do a pancake flip on it, won't it look like this with the OH dash now? See how the S one went from OH wedge to OH dash because I pancake flipped the whole molecule? And now, are these the same? Are they superimposable? They're not. And I can like start to slide them over on top of each other and see the OH is pointing the wrong direction. It's the superimposable part. So these molecules are enantiomers. And then this other one is a different type of enantiomer. Most of the enantiomers we'll see have we'll call them stereocenters, but I haven't defined it yet. They have tetrahedrons with 4 different things attached to them, like an OH, a methyl, a H, and a phenyl. So most of our enantiomers will be tetrahedrons like this, but they don't have to be tetrahedrons. Here's an example that isn't a tetrahedron, this allene type of structure. Remember we did the sigma and pi bonding diagrams for allene where we said, oh, this upper carbon here has the p orbital coming out of the plane at us. The middle is sp hybridized, has a p orbital coming in and out of the plane, that pi bond's there. And it also has a p orbital in the plane that pi bonds with this p orbital in the plane. So these have to be opposite sides. All right. So these two molecules have the same formula, same connectivity, but they differ in three-dimensional arrangement. And they're not this, and they are different molecules. I'll prove down below. And their mirror images, the bromine's looking in the mirror, the methyl, H. So these are enantiomers as well. And let's see that they're mirror images. If I take this one here, the left one, it's got the methyl on the left, bromine on the right, methyl left, bromine right, dashed hydrogen, wedged methyl, dashed hydrogen. And I do another pancake flip or rotation around the middle there. You see how the bromine and the methyl switch sides, and then the hydrogen, the methyl that was wedged is now dashed. Does that rotation make sense? So this is still the same molecule. I just, pancake flipped or rotated about that axis. And you can see it doesn't match up with this one because bromine and methyl will match up, but the wedged out methyl here on the bottom doesn't match the dashed methyl there on the bottom. So those two are enantiomers, even though they don't have a tetrahedral center with 4 different groups. Still, the definition is just, are they stereoisomers and mirror images? They're enantiomers. So yeah, this side contains what we call a chiral center. We'll define that shortly, or a tetrahedron with 4 different groups. And this one does not contain your typical chiral center with a tetrahedron of 4 different groups. Okay, and then now for diastereomers. So what are diastereomers? Non-superimposable stereoisomers that, and they do not have what? They are not mirror images of each other. Okay. Oh, I'm sorry. I have too much Zoom chat and windows going on to see what I'm clicking through here. So 3-pentanone. It's a ketone, pentenone, ketone and an alkene. So you can see they have the same formula, but this one has got 1, 2, the ketones on 2, and the alkenes 1, 2, 3, starts at 3. We'll talk about nomenclature of these in chapter 9. No, it'll be later, not for a while, but you're just seeing them now for the first time. So these are what? They're stereoisomers for sure. Are they mirror images? Is this ketone and this ketone a mirror image? No. So they're diastereomers. And this one on the left is the trans, because you can see they're trans from they're on opposite sides. And then this one's the cis. They're also referred to as E and Z. I'll define those later. I know I'm doing a lot of this. I'll define those later, but I will. And when later, after I've done those definitions and you come back through this, you're like, oh, I get it. And then this ones here, these have our more common tetrahedral stereocenters, we call them, tetrahedrons with 4 different groups. So I have one here, this tetrahedron. It's a mirror image of the other one, right? Can you see that? Is the bottom one with the bromine and the alcohol, are they mirror images to each other? No, this bottom tetrahedron is not a mirror image to the other one because the bromine is not matched up right with the OH, right? So these two molecules, they're mirror images on part of it, but not the other part. So they are not mirror images. They have to be perfect mirror images all the way through. So these are stereoisomers that are not mirror images. They are diastereomers as well. And this first example with the alkenes, they don't contain those chiral centers or stereocenters, the tetrahedrons, but this one does contain that. So I just wanted to point out that you can have diastereomers whether or not you have these tetrahedral centers with 4 different groups. Okay, some of these statements here, they're probably like kind of half making sense, but it's still good to see it now. And then as we go through more and you come back to it, you're like, oh, now I see the sign. Okay, Examples of a meso. Before I do meso, let's do some more. Let me pause on this meso stuff. Any questions so far? Okay, so I'm gonna go over to the Jamboard. The meaning of life is, I think it's 137 or something like that. Okay, so now let me talk to you a little bit more about the stereochemistry. Why are we making such a big deal about it? Why do we care? And I'll use my two I used before, my two tetrahedrons. Let me stop the screen share temporarily. So I've got these two molecules. I showed that they're non-superimposable because no matter how many times I tried to match up everything, so I can match up two of the colors, the blue and the yellow, but then the red and the green do not match. They're off, right? So these two molecules are different molecules, same molecular formula, same connectivity, but they're mirror images. Let's go mirror images. It took me a while. They're mirror images to each other. So these are enantiomers. So I've got these two here. Same ones as before. Let's make sure they're still enantiomers. There it is. Yes, they are not superimposable. I can put the red and the green together, but the blue and the yellow are off. But if I switch them around, I'm like, oh yeah, I'm gonna make them the same. So yellow and blue are the same. Yellow and blue are the same, but then the red and the green are wrong. So you can't make them. Same molecular formula, same connectivity. They are mirror images. So they are enantiomers. Now, if I take my left-handed one, I don't know if that looks left-handed to you, but if I put that one down here and I take the other one, just one of them, and I switch any two colors, I'll create the other molecule. I'll show you. So if I can find my text. Nope, I don't want to do that. I want to go to my chat. Okay. Got the chat back up. So what colors would you like me to switch? It can be any two. It's like I'm doing a card trick. Pick two colors for me to switch. Green and red. Okay, here's the green. I'll take this green off and I'll put the red in the green spot. The red is going onto the green spot. And the green's going back where the red was. All right, and now I'll pick up my other one and see now if they're the same. So if I match up my green and my red, oh, look at that, they're the same. See how all of them match up, even the green above. So these two now, by switching two colors, I create the other one. So they are superimposable. That's the big word. They superimpose on each other. And it's just a fancy way of saying they're the exact same thing. So are these isomers now? No, they're not isomers. They're exact same molecule. Isomers are different molecules. Okay, so yeah, they're the exact same thing. Now, if I take either of them and I switch any two, will they be the same still? No, so let's check. Okay, I'm gonna take this one. So this one here, what two colors do you want me to switch? Red and blue, okay. Red and blue. I'll take off the blue, set it down, take the red off, put it on the blue side, put the blue side, blue on the red side. What was the red side? Okay, so now are they the same or different? Let's see. I can match up the red and the yellow. Oh, but then my blue and green are not the same, huh? I'll fix it. I can do it. Just give me a minute. Just give me a minute. Here we go. Just oh, red and blue. There you go. Blue and green. Blue. Oh, the red and yellow are wrong, but the blue and green are right. Okay, red and yeah. Let's do the red. Let's do the yellow and green. If I do the yellow and green, it'll work. I know it'll work. It's gonna work. Yellow and green. No. I think it's funny when you give someone a challenge and then they're like competitive about it and they won't take help. They'll keep trying and they'll get frustrated, and even though it might be an impossible task. So yeah, we got that. So these two are different. Are they mirror images? Yeah. Twist this around like so. Boom, they're mirror images. Yep. They're mirror images that way, that way. I go like this. They're mirror images. Yep, mirror images. Enantiomers. Now we know these enantiomers. What seems more similar to you, enantiomers or diastereomers? What do you think's more similar? Yeah, the enantiomers are so similar. They're mirror images. Where diastereomers, they're really similar, but they're not mirror images. So enantiomers are kind of more similar. And if I just like have one and the other, and I say, oh, how do I tell you which one I'm holding? Like, oh, this one is this one. I guess if I hold it by the yellow and the red is pointing at my face, the blue has to be wedged out and green in the plane. That's this one. If I hold this one by the yellow, red pointing at me, blue pointing at you, green would be on the other side. So we have to come up with a way to name them is what I'm getting at. And so there was some chemists who sat down and they came up with a nomenclature for these. It was a guy named Kahn and then another Ingold and Prelog. So there's the Kahn, Ingold, Prelog nomenclature rules for stereocenters. But actually, I have to tell you what a stereocenter is first too. So let's do that. The honor students had this as their tryout. So I'll just have them take over. So who'd like to speak first? Annalise, Brandon, not Annalise, Aliana, Brandon, who'd like to teach this part of the lecture? Just kidding, I'll teach it. Here we go. So I want to make sure I spell this right. Kahn, Ingold, Prelog. I think it's K-O. No, I think it's C. C-O-N-H-E-N-G-O. There it is, C-A-H. Yeah, let's see. Priority rules. So this we use to assign absolute for stereocenters. And stereocenters are also known as chiral centers or asymmetric centers. So absolute configuration stereocenters. There's a lot in this definition that you're like, what's going on here? I mean, there's not even the definition, just the terms. I'll help you. Let's break it down. Stereocenter. So a stereocenter is a tetrahedral atom with 4 different groups. Let's try to make up some examples, see if we have some stereocenters here. Getting the iPad going. Okay, so does this molecule have any stereocenters? Actually, I'll add one more here. Let's go. So what we have to do is each atom, it's usually a carbon, we have to look at it and say, okay, first, is it a tetrahedron? And then does that tetrahedron have 4 different things attached to it? So this guy right here, this carbon number 1, I'll number them too. 1, 2, 3, 4, 5, 6, 7. I'll call it like A. Okay. So does carbon 1, is it a tetrahedron? Yes. Does it have 4 different things? What do you think? No, it has 3 hydrogens. 3 identical hydrogens, right? So nope, it's not a stereocenter. Okay, how about carbon 2? Is that a stereocenter? Is it tetrahedral? Nope. That's not a stereocenter. Carbon 3. Tetrahedral? Yes. 4 different things attached to the tetrahedron? No. It has 2 hydrogens that are identical, so they're not different to each other. So it's not a stereocenter. Okay, carbon 4. Is it a tetrahedron? Yes. Does it have 4 different things attached to it? Well, what do you think? Let's see what the votes are. Does it have, what do you think on the chat? I'm watching. Do you think it has 4 different things attached to it? I haven't really defined 4 different things yet. But let me talk you through it. So carbon 4 has a bromine, it has a hydrogen, they're different. And then it has a carbon and a carbon, they're the same, but if I keep going, 2 hydrogens, still looking the same. But if I continue, then I've got another carbon looking the same. But wait, now this carbon's got 2 methyls and this has got an, oh, they are different. Yes. It has 4 different things. It is a stereocenter. It's our first one. So a lot of you were saying, no, it's not a stereocenter. It has, you were thinking, oh, I have carbon 3 and 2 that's looking the same, but you have to keep going all the way down the line. And if at any point, no matter how far it takes, if they're different, they're different. So this is a stereocenter. I usually put little asterisks by the stereocenter to emphasize them. There we go. And now carbon 5, is that the stereocenter? No. 2 hydrogens that are the same. Carbon 6. What do you think? It's almost Halloween. So carbon 6 is tetrahedral. Good. 4 different things. Aren't carbon A and 7 both methyls? Those are the same. So let me break it down. Tetrahedral. Yes. 4 different. No. Not a stereocenter. No, because carbon 7 equals carbon A, right? They're both methyls. You have 2 that are exactly the same. No. So that molecule only has 1 stereocenter in it. I tricked you again. If I would have written this question up like this, you probably would have been fine. You'd have said, oh yeah, those 2 methyls are the same. They're equivalent. Like on the NMR, this would be a 6 hydrogen doublet, huh? They're equivalent. They're not different. Isopropyl, is that? It's not, yeah, it's kind of like, that's an isobutyl. It depends on how you think of it. It's an iso group. So dashing 1 doesn't mean it's different. It's just, I just happen to draw it in 3D. Okay, so back to our definition. Let me, can I copy and paste this? It's the next slide. I don't know. Yes, I can. So once we find our stereocenters, then we have to assign priorities to those 4 different groups. So, sorry, hit it. Okay, 1, find stereocenters. 2, all right. So how do we assign priorities to the different groups? What's the criteria to say, oh, this group is higher priority than the other? Priorities are based on, that's so what is the priorities based on? Does anybody remember from an honors tryout? Atomic number. What's the atomic number? Number of protons. Then if they have the same number of protons, then you go to neutrons. Then breaks ties. Okay, so let me show you what I mean with an example. All right, does this molecule have a stereocenter? I've got a CH3 here. It's tetrahedral, but 3 hydrogens, they're all the same. It's not a stereocenter. Over here, I've got another methyl, 3 hydrogens, all the same. It's not a stereocenter. This one, maybe it's a stereocenter, it's tetrahedral, but oh wait, no, 2 hydrogens, they're the same. Not. This one though is a stereocenter because it has a bromine, a hydrogen, they're different, and then a C, they're tied, but if I keep going, I see, oh, I have 3 H's. This just has 2 H's and a C. So yeah, this is my stereocenter right here. I do have a stereocenter. Now I have to assign priorities. So I like to use letters for this. If you look online, some of the honor students I saw, they use numbers. You can use numbers too, but I like to go with letters. I'm going to call A the highest priority. And then I'll go down to D is the lowest priority. So what's the highest priority? The highest priority is the one with highest atomic number. Oh. So what's our highest priority on this stereocenter? There's 4 different groups: a bromine, a hydrogen, a methyl, and an ethyl. So the highest priority group would be what? Bromine, hydrogen, this carbon, this carbon. Bromine's the highest priority. So I'll put an A by that. Bromine's A, highest priority. Okay, what's second highest priority? Let me say this too. Bromine has how many protons? You don't normally wouldn't look this up. Atomic number 35. Normally you'd know bromine's the bigger atom, right? But $35, cool. Now, what about hydrogen's atomic number is 1, carbon's atomic number is 6, but there's 2 here. So hydrogen's definitely losing, right? But which carbon should win? This carbon or this carbon? They're tied at first. But then the carbon on the left has 3 hydrogens, and this one has 2 hydrogens and another carbon. So who should win? The methyl or the ethyl? This one wins. Ethyl wins. So it's a carbon with another carbon and 2 hydrogens, right? So this is like the first step is just that it's a carbon, and the second step it has this. Whereas on this side, this one, it's a carbon with 3 hydrogens. So in its second step, it has 3 hydrogens. So they're initially tied at their carbon step, right? But then as you keep going, this one will have 1 carbon and 2 hydrogens. This has 3 hydrogens. So this one's going to make it bigger. All right. And now the last priorities should be easy because it's just carbon, this carbon here versus the hydrogen. So carbon's obviously got a higher atomic number. This will be C, and then the hydrogen will be D. Lowest priority. Okay, we got our priorities straight. Let's finish this one off, and then we'll take a break till Monday's lecture. So edit. After you've got your priorities assigned, you have to view the molecule. 2, this will be 3. So that the stereocenter is in front of the lowest priority. So this can be the most challenging part at first when you're learning how to do this. You make sure this guy is closer to you than the lowest priority D. Is it currently closer to you? Yes. So it's ready to go. This one's easy to do. And then what you do is you just draw an arc from the A priority to the B priority to C priority. You don't include D in this arc. D is just used to orient yourself. D is just, you got to make sure you're viewing it with D away from you. And then finally, if that arc is, well, let me draw the arc really quick before I forget. So the arc for this one would be A to B to C like that, right? if the arc is clockwise, the molecule we assign the stereocenter as R. We say it's an R stereocenter. If it is counterclockwise, counterclockwise 2 words? I think so. We assign it S. So is the absolute stereochemistry of this stereocenter here, is it R or S? Is that arc there? Is it clockwise? Clockwise, so this is R. So now we can like fully name this molecule for a friend, like if you wanted to email them and not have to draw it out. This molecule is called 2R 2-bromo-butane. If this bromine was not wedged, it was dashed, this would be 2S 2-bromo-butane. Okay, we're going to do a lot more examples like that. But before I let you go, I want to show you the Deadpool viewing of this. This is one of my favorites. I updated this GSA on this morning. No, yesterday and this morning. Last night, I was helping Nick with his unit circle, his geometry stuff. He's like, why do I need to know this? I'll just do it. The unit circle really helps, right? For calculus. I think if you just have the unit circle memorized, like sine theta in the universe unit circle, if it's 45 degrees, it's the x and y coordinates are square root 2/2. That's the, yeah. All right. So while I was giving him problems to do, I was updating the Deadpool absolute stereochem. So I had an honor student, Heather Fletcher, back in 2016, and I had her make this. She made it as a PowerPoint. I've updated it a bunch since then, but I had her make this to help people visualize stereocenters the right way, because when if the lowest priority D is facing away from you, if it's dashed back, it's easy. But when it's in the plane or coming at you, it can be more challenging. And I caught the idea for this because at the time, this was 5 years ago, Nick, who's 13 now, was about 8. He was super excited about the Deadpool movie was first coming out. Okay. He was excited for the Deadpool movie coming out. And we were like, yeah, Nick, you're a little young to watch the Deadpool movie. But then he would watch all the trailers online. So it's like he watched the whole movie. And then he went to some YouTube website, taught you how to draw Deadpool. I like those websites. Ryan probably seen those. They teach you how to draw like whatever, they slowly work through it. You can pause and draw. So he was into drawing for a little bit. I wish he would do more because he was good at it. But video games are too powerful. They're a black hole of a kid's time these days. But so he was drawing them, and then I thought, oh, I'll use that as the idea for students to visualize stereocenters. So I asked Heather to draw them, and I gave her the YouTube videos, and she did a pretty good job. So here's the absolute stereochemistry RNS Deadpool edition. Okay, so here we go. So you have to find a stereocenter, aka it's also called a chiral center, and an asymmetric center, not symmetric. When you have A in front of a word, it cancels it. Like if it's symmetric, it's symmetric, but asymmetric is not symmetric. And then the stereocenters, or whatever you want to call them, they're tetrahedrons with 4 different groups. And you have to get your priorities straight. That's what we were talking about. And the priorities, you do it stepwise. So like if you're at a stereocenter and you go to the first set of atoms attached to it, and they're the same. You don't stop there. You keep stepping down the line. And then you use atomic number to rank, prioritize. So the higher the atomic number, the higher the priority. Lowest priority is D. And the D, the lowest priority, is only used for orientation, just to like set the molecule up right where you're like with the D pointing away from you. So here we go. In this example, my lowest priority is where? Is it pointing at me or going away from me? Now it's going away from you, right? So this is the easy orientation, because when the D is pointing away from you, the stereo center is closer to you, so you're already viewing it correctly. You just have to draw an arc, A, B, C, and view it. And if it's clockwise, it's R. If it's counterclockwise, it's S. And now in this one, where's the D? Is it pointing away from us the easy way? No, it's pointing in the plane of the page. So we have to imagine that we are in the plane of the page like this. So when I look like that eyeball there, I see the D. A is up above, B is to my left. So this one is S. Yeah, A, B, C is S. Yep. And then if D is in the plane and up, you have to imagine you're underneath it, that you're in the plane underneath the molecule. And it's A, B, C. This one is R. Yeah, R. Yeah, that one's R. And then if D is going at you, if it's wedged out at you, now you have to imagine you're behind the molecule. So I'll throw in some eyeballs back here. You're behind the molecule, you're not in front of it or on the side. And that particular one, it's going to be S. Yeah, that one's going to be S. When you view it from behind, it'll be S. Okay, and then once you have, well, I actually jumped ahead. The ABC, those are used as your only for the arc. Once D orients you, then the ABC draws the arc. So if the arc is clockwise, ABC coming around like that, the molecule is R. If it's counterclockwise, the molecule is S. And S is, it's interesting. People refer to the R molecules as right-handed molecules and the S as left-handed. I know I can show you a reason for that. But then S, it's interesting, the S is for sinister, because back in the day, people thought, oh, left-handed people, they're different. Most people are right-handed. So left-handed is wrong. They're sinister. They're left-handed. They're bad. So I don't think that. It's actually better to be left-handed if you want to play baseball. Like most baseball players are left-handed, I think, because left-handed pitchers and hitters have an advantage. Left-handed hitters are already closer to first base. So interesting, the old times sayings. So now for the Deadpool viewing. So this one, the D is coming out at us. So you have to imagine your Deadpool. He's going to try to shoot from behind. So don't be a bad Deadpool. Check your configurations. Good Deadpool. So see how you have to imagine you're behind the molecule viewing this. And then this one winds up. Yeah, Deadpool needs to view the molecule from behind. I don't know why that's coming up twice. It's R for it just got real. What is going on? I hope my computer's not about to crash again. And this one, the D is pointing away from us. This is an easy one, huh? You're Deadpool in this configuration, so don't miss. It's S for serious trouble. So this is A, B, C. That's going counterclockwise. And then this one, lowest priority is pointing up. Then Deadpool has to be below. And he's saying, now I'm about to do to your configuration what Limp Bizkit did to music in the late 90s. It's S for sinister. Yeah, A, B, C. Yeah, that's S. And then here, D is in the plane to the left. Crimes the disease, meet the cure. Okay, not the cure, but more like a topical ointment to reduce the swelling and itch. Here we go. S is for seriously? You're paying money to watch a grown burnt man in red tights? Okay, Ryan Reynolds would have read it better, but that's okay. Great work. I'm so proud of you. Now, how about a crisp high five?